wanted to start with the three heroes of the previous three industrial revolutions. And to every age, a relic. And the relics of the three first industrial revolutions were the steam engine, the Ford Model T, and the personal computer. Now, there's one common denominator that brings all of these relics together, and that is that they are made of parts, they are assembled out of parts, and that they are ecology indifferent. In the process of their design, their designers haven't brought into account how might they affect the ecology, their natural environment, in the way in which we can today consider these kind of effects. So since the Industrial Revolution, the world of design has been dominated by a culture of parts. Designers and architects have been trained to think about their designs in terms of assemblies of discrete parts made of homogeneous materials. But we know that nature doesn't operate this way. And when you think about the natural world, when you think about both the biological and the organic, the plant world, you see wholes that are made not of assemblies, but of heterogeneous parts that constantly and continuously vary their properties. So for example, the skin varies its porosity, its elasticity, its stiffness, right? Its melanin concentration, its color. So as designers aiming to move beyond the age of the machine that has been so characteristic of the first three industrial revolutions, we find ourselves stuck between two representations of the world. A representation that is two-dimensional or binary, the representation of the digital world, and the representation of the biological world, that is a quadrocode representation made of the four base pairs. So the binary and the biological, the digital and the biological. And as designers today, we're attempting to integrate between the material, the digital, and the biological domains in order to create products, buildings, and cities that are non-ecology agnostic, that are non-ecology indifferent. So you could think about this as a kind of a duality or a dichotomy between the world of culture and the world of nature, between the world of assembly and the world of growth. True that some of you, the biologists in the room, may claim that growth is a kind of automation without assembly, an automation that is self-assembled. But I'm going to tackle this kind of dichotomy and propose to you a new kind of thesis for design. That is, as designers, we must today bring into account not only the digital, but also the biological. So I had a group at the MIT Media Lab called Mediated Matter, and we operate at the intersection of the material, the physical, the digital, and the biological. These are the four fields inside which we operate. And today I'm going to take you through a very brisk and fast and rapid journey throughout some of our products, and I've sort of organized the projects in an order of complexity, so they become more and more complex. We start with projects that are inspired by biology, projects that are informed by biology, engineered by biology, designed by biology, and end with projects that design biology herself. So from nature-inspired design to a design-inspired nature. So let's start with the very, very first set of projects inspired by the natural world. This was a dress that we've designed for Paris Fashion Week in 2012, 2013, and the dress was inspired by the human skin. Again, instead of generating an assembly that is made of parts and that are sewed together, we're designing a continuous cape and skirt that can vary their porosity, the length of the parts, their direction, their material composition, to provide a wearable that is both structural and also comfortable, but can also filter air and potentially sweat. So again, a single system that varies its properties continuously rather than an assembly of parts. This object, as many of the ones that I'll show in the presentation today, were printed with Stratasys digital materials technology, and their digital materials allowed us to design with preset mechanical combinations, so a wide array of mechanical and optical properties that were integrated into this wearable. Another project was a helmet that was designed for my head, can be designed for any head. This particular helmet, its design is interesting because it allows us to design not only for the shape of the head, but also for the material composition. So rather than only taking the geometry of the head as an input, you're taking as input the physiological components that make up your bone, your fatty tissue, your muscle tissue, and you can respond to that in very high resolution. So you can arrive at a helmet that is both protective, that is shock absorbent, but is also comfortable. You're mixing and fusing stiff and soft materials together in very high resolution, 16 micron voxel resolution. This is the diameter of the human hair. It's also the diameter of the largest mammalian axon nerve ending known. And so because you have access, because we as designers have access to such high resolution tools and synthesis, we could map between a CT scanner and a 3D printer. Okay? And we can also combine light in it. So again, rather than generating assemblies, we're generating continuities. This chaise was designed for the Dalai Lama, hence the colors. It was a chaise that was designed to quiet the thinking mind, and it was designed out of 44 different materials with preset mechanical combinations that vary in rigidity and opacity and color and respond to the pressure points around the body, a little bit like wearing your acupuncture therapist or sitting in the room, but really a very, very quiet environment that's completely sound absorbent. So from inspired by nature to informed by nature, and also moving up in scale from products to buildings, we ask ourselves, how can we implement some of these principles in architectural scales? Can we design buildings made of concrete that are inspired by the bone, where we're varying the porosity of the bone, in this case of the concrete, as a function of the load? Can we, for example, print variable density concrete that is sensitive to a loading condition of a building such that we save material and also design in a new kind of aesthetic, a new kind of design language? So this is the first robotic system that's completely mobile. It's called the Digital Construction Platform. And it is a platform that is designed to additively manufacture a building, hopefully in a single day, on site, continuously as the printer goes about the site. This is a long exposure photograph just to show you the range. This is an 80 feet diameter range for a large-scale robotic arm, a hydraulic arm that's connected to an electric arm, 5 and 6 degrees of freedom that allow us 11 degrees of freedom on site. And now what's interesting is that these two arms, the hydraulic and electric arms combined, are not only used to deposit materials, but they're also used to scan the environment. So they're used to capture analytic data from the environment, such as optical data, thermal data, magnetic waves, electromagnetic waves, and incorporate this data as part of the fabrication process. So think, for example, about the prospect of mapping or scanning seismic loads, incorporating that on the fly in the printing process, and being able to design and print a building that corresponds to these environmental conditions. So again, analysis and synthesis come together in a single tool, in a single compound fabrication technology. But additive manufacturing is today suffering from the material bottleneck. Many of the materials that we use are still toxic, non-environmentally friendly. And to that end, we've started looking into the prospect of using biodegradable and or biocompatible materials for printing. We specifically focused on chitin. Chitin is the second most abundant biopolymer on the planet, after the first most abundant, which is cellulose. Yes, and it's found in crustaceans such as shrimp shells and butterfly wings. And what's fascinating about this material is that in this exoskeleton of these organisms, you find very stiff shells that become 100 times more compliant when they reach their root. So again, they vary their elastic moduli, their stiffness ratios, very, very quickly in a single system. We wanted to mimic this in the design of products and wearables, and also hopefully building parts. And so we've ordered many kilograms of shrimp shells. We grinded the shrimp shells, and we've generated chitosan by deacetylizing the chitin. And this chitosan allowed us to print in a range of mechanical and optical properties within a single process, similar to the way that nature does it. So here you can see the platform. It's a mixing nozzle that in this case contains 5 jets that can vary these properties on the fly. We're printing them flat, and as we take them off the dry rack, they find their form naturally upon contact with air. So these structures have been, in a way, made by water from entirely natural materials that are completely and entirely recyclable. So 40 megapascals at the root, soft, very soft at the edge, and inspired again by the crustaceans that are made of chitin. These structures combine skin and structure in a single element. Now think about the prospect of getting rid of plastics, right? Less than 5% of plastics is actually recycled. And imagine what it would mean to start generating your Starbucks coffee out of chitosan or a Whole Foods bag out of chitosan and let them biodegrade naturally in the rain, nourish the fisheries, help grow trees. And this kind of material ecology begins to consider the material world as part and parcel of the natural world. No more separation between products and the natural environment. One of the byproducts of this printing process was that we got lots of air bubbles in our products, which we tried without much luck to get rid of. And we thought, well, every problem brings about its own opportunity. How about we use those air bubbles to contain photosynthetic microorganisms that could capture carbon from the environment and turn it into sugar or biofuel. So not only are we returning this material back to the environment, but we're sort of returning it with a positive carbon footprint, right? We're generating energy, we're augmenting the natural environment in addition to using a natural material. So in a sense, this is like attaching a wet lab, a chemical or synthetic biology lab to a robotic arm. And I think this is where design is going. No longer will you see designers going to work with a synthetic biology inside a lab, but the lab comes to the robot. So the robot has a scanner, it has a printer, and it has a wet lab. So let's take this a bit deeper. What does it mean to design with nature? Not only be inspired or informed by nature, but actually use natural organisms with which to design products and building parts. So in my lab, we know how to print with cells, with biological cells, embed and augment them in structures, but we also know how to additively manufacture microfluidics and millifluidic devices that can allow us to mix and match between different kinds of microorganisms to achieve different biological functionality. The same kind of principles that you've seen in the chair, in the helmets, in the dress are applied here, only instead of varying material properties, we're varying biological functionality. So we're controlling chemistry rather than just controlling material properties. So same principles, only a level deeper. In order to embed microorganisms in the body, we have to come up with computational algorithms that allow us to contain and direct the movement of those microorganisms in very high resolution. So I'm going to talk about one project that combines 2 microorganisms. The first is the cyanobacteria that lives in fresh water ponds and oceans. It's 3.5 billion years old, so it's a very old technology. And the second microorganism is E. coli, and it lives in the human gut. So now, these 2 organisms, one lives in the ocean, the other lives in our gut, never interact in nature. And so here in this project, they're brought together, they're united by design to interact in a wearable device. So I call this evolution by design. Designers now have control of evolution by natural selection, as it were. So cyanobacteria convert sunlight into sugar. E. coli consumes that sugar and produces biofuel. The biofuel can fuel your scooter, it can fuel the building, etc. So think about it as a kind of an overall material ecology where one product fuels the other. So of course, in order to contain and direct their movement, we need to design systems that can do this. So you're looking at various systems that we've been exploring. In this particular case, this system is inspired by the gastrointestinal tract to design a kind of artificial digestive system for the human body that in the future potentially will interact with the digestive system. This hopefully will enter the architectural world where we can also digest, as it were, the human environment and correspond to it. So in this case, this was the container that contained our photosynthetic microorganisms. I like this video because you can see the photosynthetic organelles inside the microorganisms. We then computationally grew these structures on the human body such that they fit the geometry of the body, but they're also responding to the biological functionality that we want to generate. So the orange represent opaque material, the white represents transparent material. In the transparent areas, we place the cyanobacteria that takes on photosynthesis, so they need to be exposed to the light, hence the variation in opacity of the container. Unfolded end to end, this wearable digestive system spans 59, close to 60 meters. This is 10 times the length of the small intestines and half time the length of a football field, all folded into a single digestive system that is wearable and generates energy for free, if you consider that solar energy is for free, which is another ethical question. So this is the wearable device. You expose your body to the sun, you generate sugar cubes in your pocket. And I like to think of it as a kind of a wearable microbiome that in the future will be able also to filter some of the chemical and biological compounds in our own body, scan our bodies, and potentially also repair damaged tissue. Because we have such access to additive manufacturing in high resolution, high fidelity of heterogeneous materialities, we can today compete with the analysis protocols. So in the past, when you would design a car, you would have access to computational fluid dynamics to be able to establish the optimal form of a building or a car wearable. But today, we could do that synthetically. So not only use a high-dimensional, high-resolution analytic tool, but also develop high-dimensional, high-resolution synthetic tools. And we can match between analysis and synthesis in very, very high resolution. This will allow us to produce better prosthetic devices, building skins, wearables that correspond and respond to the body. And this is just a teaser for one of the collection of wearables that we're about to launch in my lab that shows you how we can scan the face and compute the final breath before we die. So again, we can gain access to extremely high resolution data from the human body and design for it and with it. Designing with nature doesn't stop with a microorganismic scale, and it continues with actual organism scale. So I'm going to show you a project which some of you may know, the Silk Pavilion, which questioned additive manufacturing through the lens of biology. Biology doesn't print stuff, except perhaps oysters. But biology grows, it moves about three-dimensional space in a way that is way more complex than your traditional printer and even bioprinter. So the silkworm constructs its cocoon in 24 to 72 hours. It's one of the most sophisticated structures, definitely one of the most sophisticated architectures. And what we did is we tried to replicate this kind of logic and behavior in the construction of a bucky dome. Only now, the bucky dome would not be made of parts. It would be made of a single fiber that would vary its properties locally as a function of its structural and environmental performance. That was the goal. So that's how we went about it. We placed first to motion capture the silkworm. We superglued a tiny earth magnet to its head. It was completely healthily metamorphosized. We motion captured its movement using 3 magnetic sensors. We triangulated between those 3 magnetic fields. We generated the point cloud. And in parallel, we did studies that proved that the silkworm, once you place it on a flat patch, it will still spin its cocoon, only the cocoon will be spun flat. It would not be a three-dimensional cocoon. We said, great, that means we could use the help of the silkworms in the buildup of the pavilion while allowing them to healthily metamorphosize, unlike what happens today. in India and China and various silk farms around the world where we boil the cocoons and those silkworms die. In this case, they are integrated into the construction process. So here we go. This was the superstructure, as it were, that was woven using a robotic arm and silk. We then ordered 6,500 silkworms from an online silk farm. We fed them for 4 weeks. They fed on mulberry leaves, and after 4 weeks of feeding, they were ready to spin. We placed them at the bottom rim of the structure, and as they spin over a period of 3 weeks, they pupate and mate and lay eggs and healthily metamorphosize, and we co-fabricate by cohabitating. I like this video because it shows the different scales, robotically woven silk combined with biologically spun silk to form a structure that is, again, biologically constructed together, sort of with man-made machine technology. So 6,500 silkworms, given that every silkworm spins 1 kilometer of silk in its lifetime, together spin 6,500 kilometers. This also equals the length of the Silk Road. We only discovered this in hindsight, but it seems to. And of course, they all healthily metamorphosize. The eggs that were laid on the pavilion can be used to create 150 more additional pavilions. The last project that I want to show you is in the form of a video, so I will only introduce it very, very briefly, and then perhaps interject through the video. In the future, in the near and far future, we need to move from the wet lab and into the real world. As biologists and as designers and as designer biologists, the best way to do this is to transcend the Petri dish. And to do that, we need to form glass structures that are both stiff, structurally sound, but are also transparent and that allow us to interact with the environment. To do this, we have invented a first-of-its-kind, functionally, optically transparent glass printer that we launched a few months ago into the world. And that glass printer will, hopefully in the near future, be able to additively manufacture buildings that could incorporate biological matter and allow us to make better use of solar energy in the scope of this kind of material ecology approach to design. You're looking at the printer. This was the printer that was designed and architected from scratch in my lab. It was a collaboration between Mediated Matter, the Glass Lab at MIT, and the Mechanical Engineering Department at MIT. Before I show the video, this is how the printer is designed. It has a kiln cartridge that allows us to take in molten glass and control the gradient of temperature, thereby controlling the viscosity of the glass, thereby controlling the geometry of the deposition. So it has a crucible kiln. It has a kiln around the nozzle with thermocouplers that allow us to control the variation of temperature as we're controlling the viscosity. Let's play the video, and I hope you enjoy. I will interject with a few words as it's played, so please volume up. Thank you. So the top chamber is the kiln cartridge that allows us to turn the 3D printer into a mini glass lab. And it goes about this continuous deposition of layers with a 1900 degrees temperature. This system is also connected to a form generation algorithmic environment that allows us to design the shapes and the parts that we want to print and immediately quantify and qualify how many layers, how much material, and how quickly we can generate it. this is interesting. When you pour molten glass at an offset, you get these really interesting autocoiling patterns. This is basically the structural instability of the glass. It's what happens when you pour honey on toast. And these patterns could be used to control the geometry that is at the external surface, but also in the internal surface of the product, unlike glass blowing, which only allows you to control the external surface. So these are some of the caustic patterns that were generated as you shine light through the piece. It's interesting to consider the inverse process, where you start with a shading pattern of a building or a city, and you inform the shape of the building according to a sun path diagram. So I'm going to end here with a single slide that to me represents nature. Two great maps, two of the greatest maps that were drawn by us. The first treats nature as a geological resource, that is the table of the elements. The second looks at nature as a biological resource, that is a map of the human genome. Of course, it should represent all species. And those two maps really are the material in the hands of designers today that are shaping the built environment with a true sensitivity to what biology is and what it wants to become, and that kind of transition that takes us, as I like to say, from an age where we personified nature as a mother, from mother nature, from the noun to the verb, to mothering nature, to being able to design with and for nature. So thank you very, very much.